What if I told you that right now, as you're watching this video, somewhere in the universe, two monsters are locked in a death spiral, so violent that they're literally tearing the fabric of space and time itself. And when they finally collide, they'll release more energy in a fraction of a second than all the stars in the observable universe combined produce in that same moment. Here's what will blow your mind even more. We've actually heard this happen. Not seen it, heard it. And what we heard changed everything we thought we knew about reality. On September 14th, 2015, at exactly 9 hours 50 minutes and 45 seconds UTC, two black holes that had been spiraling toward each other for millions of years finally merged. The collision sent ripples through space-time that traveled across 1.3 billion light-years of empty space and arrived at Earth, where scientists detected something that Einstein himself thought would be impossible to ever observe. The detectors at LIGO, the Laser Interferometer Gravitational Wave Observatory, picked up a signal that lasted only a fifth of a second. In that chirp, that brief cosmic scream, we heard the sound of space-time itself being shredded and reformed. But here's the truly insane part. Those two black holes, with masses 29 and 36 times that of our Sun, didn't just merge. They created something that weighed less than both of them combined. 3 entire solar masses just vanished, converted into pure energy, released as gravitational waves. That's equivalent to converting 3 times the mass of our entire Sun into energy in less time than it takes you to blink. Think about that. Where did that mass go? How can two things merge and weigh less than they did separately? And if space-time can ripple like water, what does that mean about the reality you're experiencing right now? Before we dive deep into this cosmic mystery, do me a favor. Hit that like button and subscribe, because what you're about to learn will fundamentally change how you understand the universe. And I want to know, drop a comment telling me what country you're watching from and what time it is there right now. Because no matter where you are on this planet, the gravitational waves from merging black holes are passing through your body at this very moment, and you can't feel them. Let's begin. To understand how two black holes can merge, we first need to wrap our heads around what a black hole actually is. And I need to tell you right now, forget almost everything you think you know. Most people imagine a black hole as a cosmic vacuum cleaner, sucking everything nearby into oblivion. But that's not quite right. A black hole isn't a thing in space, it's a place where space itself is broken down. Let me explain it like this. Think of space-time as a trampoline. When you place a bowling ball on a trampoline, it creates a dip, a curvature in the fabric. A marble rolling nearby will curve toward that bowling ball because it's following the bent surface. That's basically how gravity works according to Einstein's general theory of relativity, published in 1915. Mass curves space-time, and objects follow that curvature. Now imagine you keep adding more and more mass to that bowling ball. The dip gets deeper and deeper. At some point, the dip becomes so steep that the marble, once it crosses a certain point, can never roll back out. It will always slide down toward the center, no matter how fast it's moving. That point of no return is what we call the event horizon. But here's where it gets weird. A black hole isn't actually a hole at all. It's more like the universe's ultimate trap door. Once you cross the event horizon, all paths through space-time lead in only one direction, toward the singularity at the center. Not because something is pulling you, but because space itself only flows inward beyond that point. The mathematician Karl Schwarzschild figured this out in 1916, just months after Einstein published his theory. Schwarzschild was serving as a German artillery officer during World War I when he read Einstein's equations and, despite being in the trenches, managed to find an exact solution that described what we now call black holes. Tragically, Schwarzschild died just a few months later from a disease he contracted at the front, never knowing that his solution would become one of the most important discoveries in physics. The Schwarzschild radius named after him tells us how small you need to compress a mass for it to become a black hole. For Earth, that radius is about 9 millimeters. Compress our entire planet down to the size of a marble, and it would become a black hole. For the Sun, the Schwarzschild radius is about 3 kilometers. For those two black holes that merged in 2015, their event horizons were each about 150 kilometers across. Now here's something that will mess with your head. From the outside, you can never actually see anything cross the event horizon. If you watched a friend fall into a black hole, you'd see them slow down as they approached the event horizon, getting redder and dimmer, frozen at the edge for eternity. But from their perspective, they'd cross the event horizon in finite time, not noticing anything special about that moment until the tidal forces started stretching them like spaghetti. This is where things get truly bizarre. Black holes aren't just objects in spacetime. They're wounds in the fabric of reality itself. At the singularity in the center, our equations break down completely. Density becomes infinite. Spacetime curvature becomes infinite. The laws of physics, as we understand them, simply stop working. And we're about to talk about two of these reality-breaking monsters colliding with each other. So how do two black holes even find each other in the vast emptiness of space? Here's what will blow your mind. They don't really find each other. They create each other. Most merging black holes start their journey together as a pair of massive stars orbiting each other, what astronomers call a binary system. These stars are born together from the same cloud of gas and dust, spending millions of years in a gravitational dance. When stars massive enough, at least 20 times the mass of the Sun, reach the end of their lives, they explode as supernova, and their cores collapse into black holes. But here's the fascinating part. That explosion doesn't break up the binary system. The two black holes remain in orbit around each other, often separated by distances comparable to the size of our solar system. And then the spiral begins. According to Einstein's general relativity, when massive objects orbit each other, they create ripples in space-time gravitational waves. These waves carry away energy from the system. Think of it like this. Imagine spinning around in water with your arms extended. You'd create waves in the water, and those waves would carry away energy, eventually slowing you down. That's essentially what happens to orbiting black holes. As the black holes lose energy to gravitational waves, their orbit shrinks. They spiral closer and closer together. But here's the thing. This process is excruciatingly slow at first. The two black holes that LIGO detected in 2015 probably spent hundreds of millions of years gradually spiraling toward each other. For most of that time, they were so far apart that they lost energy incredibly slowly. A typical binary black hole system might lose only a few meters of orbital separation over the course of a year during the early phases. But gravitational wave emission increases dramatically as the objects get closer together. The power radiated goes up with the inverse fifth power of the separation distance. What does that mean in practice? It means that for most of their life together, the black holes barely move closer. But once they get within a certain distance, about 100 times their Schwarzschild radii, things start accelerating rapidly. Astrophysicist Kip Thorne, who won the Nobel Prize in Physics in 2017 for his contributions to LIGO, described this process beautifully. He calculated that in the final second before merger, the two black holes are orbiting each other hundreds of times per second, moving at speeds up to 60% the speed of light. Imagine that, objects each containing 30 times the mass of our Sun, spinning around each other hundreds of times every second. The gravitational waves they emit during this final moment carry away more power than all the light emitted by all the stars in the observable universe combined. For that brief instant, the merging black holes are the brightest thing in the universe, not in light, but in gravitational radiation. Here's something to think about. As you're sitting there watching this video, gravitational waves from countless merging black holes are passing through your body. Right now, waves that started their journey millions or billions of years ago, when those black holes began their death spiral. These waves are stretching and squeezing space-time by impossibly tiny amounts, about 1/10,000th the width of a proton. You don't feel them because they're so weak by the time they reach us. But they're there, a cosmic background hum of colliding monsters. Before we continue, I need you to understand something. We're about to get into the really mind-bending stuff. The moment of merger itself, where the math gets truly strange and reality becomes almost incomprehensible. If you're enjoying this journey, make sure you're subscribed because we're going deeper than you ever imagined. Let's talk about what happens in those final moments before two black holes merge. Because this is where physics gets absolutely wild. As the two black holes spiral closer and closer, each moving at significant fractions of the speed of light, something remarkable happens to space-time around them. Remember, these aren't objects moving through space. They're regions where space itself has become infinitely warped. And now two of these warped regions are colliding. Physicist Kip Thorne worked with computer scientists to create simulations of this process, and what they found was stunning. The two event horizons don't just smoothly merge together. They actually create a bridge between them just before they touch. Space-time becomes so warped in the region between the black holes that it forms a connection, throat of space-time linking the two horizons. Think of it like two whirlpools in water, getting close enough that they merge into one larger whirlpool. But remember, we're not talking about water here. We're talking about the fundamental fabric of space and time itself. In those final milliseconds before merger, the black holes are moving so fast and creating such intense gravitational fields that the distinction between them starts to blur. The event horizons begin to deform, stretching toward each other like two drops of water about to merge. And then they touch. The moment of contact is called the common horizon formation. A single, unified event horizon suddenly appears, encompassing both black holes. But here's where it gets truly bizarre. Inside that common horizon, the two singularities, those points of infinite density, where the laws of physics break down, are still separate for a brief moment. What happens next is something we can only understand through computer simulations, because the mathematics is so complex. The newly formed event horizon isn't spherical. It's wildly distorted, covered in ripples and bulges, looking almost like a wobbling water balloon. This newly merged black hole is far from equilibrium. Over the next few milliseconds, the black hole settles down. It radiates away the distortions as gravitational waves, eventually settling into a perfect sphere, or if it's spinning, an oblate spheroid. This process is called ring-down, and the gravitational waves emitted during ring-down have a specific frequency that depends only on the mass and spin of the final black hole. Here's what's absolutely insane. We can use these ring-down waves to test Einstein's theory of general relativity in the most extreme conditions imaginable. The frequency and decay time of the ring-down are predicted exactly by Einstein's equations. When LIGO detected the ring-down from the 2015 merger, it matched Einstein's predictions perfectly. A theory developed by one man in 1915, using nothing but thought experiments in mathematics, accurately described what happens when two of the universe's most extreme objects collide, something Einstein himself thought would be impossible to ever observe. But remember that missing mass I mentioned at the beginning? Those three solar masses that just vanished? Let's talk about where they went. During the final moments of the merger, the two black holes were radiating gravitational waves so intensely that they were converting mass directly into pure energy, the energy of space-time vibrations. Einstein's famous equation, E equals mc, tells us that mass and energy are equivalent. In this case, about 5% of the total mass of the system was converted into gravitational wave energy. To put that in perspective, the sun has been shining for 4.6 billion years, converting mass into light through nuclear fusion. In that entire time, it has converted less than 0.1% of its mass into energy. These two black holes converted 5% of their combined mass into energy in less than a second. The peak power output during the final moment of merger was about 1,049 watts. That's 10 followed by 49 zeros. To give you a sense of scale, that's more than 3 times the power output of all the stars in the observable universe combined, emitted by a region of space smaller than a large city. And all of that energy went into shaking space-time itself. Let me tell you about one of the most remarkable achievements in human history, the detection of gravitational waves. For decades, scientists knew that gravitational waves had to exist if Einstein's theory was correct. But Einstein himself calculated that they would be so weak by the time they reached Earth that detecting them would be practically impossible. He wrote in a letter, gravitational waves would be so weak that we should never hope to observe them. Einstein was almost right, almost. The problem is this: even the most violent cosmic events produce gravitational waves that, by the time they travel millions or billions of light years to reach us, have been diluted to almost nothing. When those waves from the 2015 merger passed through the LIGO detectors, they stretched and squeezed the 4-kilometer-long arms of the detector by a distance of about y-18 meters. Let me help you understand how small that is. If you took the distance from Earth to the nearest star Alpha Centauri, about 4.3 light-years away, and measured it with the precision LIGO needs, you'd have to be able to detect a change smaller than the width of a human hair. Actually, that's not even quite right. It's worse than that. The change LIGO detects is about 1/10,000th the diameter of a proton. A proton, the thing that sits in the nucleus of an atom, which is itself incomprehensibly tiny. How do you build a detector that's sensitive? How do you distinguish a signal that's small from the countless sources of noise that exist? The rumble of traffic? Earthquakes on the other side of the planet? Ocean waves? Someone walking near the facility? This is where the genius of LIGO comes in. LIGO actually consists of 2 detectors, one in Hanford, Washington, and one in Livingston, Louisiana, separated by about 3,000 kilometers. The detectors are identical L-shaped structures with arms 4 kilometers long. Here's how they work. Think of it like this: a laser beam is split and sent down each arm. The beams bounce off mirrors at the ends of the arms and come back to recombine at the vertex. If a gravitational wave passes through, it stretches space in one direction while compressing it in the perpendicular direction. One arm gets slightly longer while the other gets slightly shorter. This changes the pattern of how the laser beams recombine, creating a measurable signal. But here's the crucial part. For the signal to be real, it has to appear in both detectors, separated by 3,000 kilometers, at times consistent with a gravitational wave traveling at the speed of light. Random noise won't do that. Earthquakes won't do that. Trucks driving by won't do that. The scientist who really made LIGO possible was Rainer Weiss, a physicist at MIT. In 1972, Weiss wrote a paper that laid out in extraordinary detail exactly how you could detect gravitational waves using laser interferometry. He didn't just describe the basic idea, he calculated every source of noise, every possible problem, and how to overcome them. That paper became the blueprint for LIGO. But even with Weiss's brilliant design, it took decades to make it work. LIGO was first funded in 1992. The initial detectors started taking data in 2002. They ran for years and detected nothing. The original LIGO wasn't sensitive enough, so they upgraded it. Between 2010 and 2015, they performed a massive upgrade called Advanced LIGO, improving the sensitivity by a factor of 10. The upgraded detectors began their first observing run on September 14, 2015. And on that very day, literally, the first day of operation, they detected a signal. When the signal came in, many of the scientists thought it was a test. The LIGO collaboration has a policy of occasionally injecting fake signals into the data stream to keep the analysis teams on their toes. But this wasn't a test. This was real. The signal lasted only 0.2 seconds, but it contained a complete story. For the first 0.15 seconds, the frequency gradually increased the chirp as the two black holes spiraled together, orbiting faster and faster. Then came the merger itself, followed by the ring down of the final black hole settling into its stable form. The scientists spent months analyzing the data, checking and rechecking their work, ruling out every possible source of error. On February 11, 2016, they announced the discovery to the world. It was the first direct detection of gravitational waves. It was the first direct observation of black holes merging, and it opened up an entirely new way of observing the universe. Think about this for a moment. For all of human history, our astronomy has been based on light. We look at the light from stars, galaxies, planets. Even with radio waves, X-rays, and gamma rays, we're still just detecting different forms of electromagnetic radiation, different forms of light. But gravitational waves are fundamentally different. They're not electromagnetic radiation at all. They're ripples in space-time itself. They let us observe events that produce no light, that are completely dark. They let us hear the universe instead of seeing it. And what we're hearing is just the beginning. Since that first detection in 2015, LIGO and its European counterpart Virgo have detected dozens of black hole mergers. And here's what's fascinating. No two are exactly alike. Let me tell you about some of the most remarkable ones, because each one teaches us something new about the universe. In 2017, LIGO detected a merger that was different from all the others. The signal was longer, lasting several minutes instead of a fraction of a second. When scientists analyzed it, they realized they weren't watching two black holes merge. They were watching two neutron stars collide. Neutron stars are what's left when a massive star explodes as a supernova, but isn't quite massive enough to form a black hole. The core collapses into an object about the size of a city, but containing more mass than the sun. They're so dense that a teaspoon of neutron star material would weigh about 1 billion tons. When two neutron stars merge, something magical happens. Unlike black holes, which are completely dark, neutron star mergers produce light. Lots of light. Telescopes all over the world and in space swung into action, observing the merger in gamma rays, X-rays, ultraviolet, visible light, infrared, and radio waves. What they saw was a cosmic forge. The collision created conditions so extreme that it synthesized heavy elements like gold, platinum, and uranium. In fact, scientists estimate that a single neutron star merger produces more gold than exists in all of Earth's crust. Think about that. The gold in your wedding ring, the platinum in catalytic converters, the uranium in nuclear reactors, all of it was created in the violent collision of neutron stars billions of years ago. You're literally wearing debris from cosmic catastrophes. But let's get back to black holes, because LIGO has detected some truly bizarre mergers. In 2019, they detected a merger between a black hole with 23 solar masses and one with 13 solar masses. But when they analyzed the signal carefully, they noticed something strange about the smaller black hole. It was spinning, fast, and not just spinning, it was spinning at an angle relative to the orbital plane. Imagine two dancers spinning together, but one is also spinning on their own axis at an angle. That's essentially what was happening with these black holes. This tells us something important. These black holes probably didn't form together as a binary star system. They likely formed separately and met later, possibly in the dense environment at the center of a galaxy where black holes are common. Then, in 2020, LIGO detected something that shouldn't exist according to our understanding of stellar evolution. They observed a merger involving a black hole with about 85 solar masses. The problem? Stars that would create black holes that massive shouldn't be able to form them. Here's why. When very massive stars, more than about 60 solar masses, reach the end of their lives, they explode so violently that they completely blow themselves apart. Nothing should be left behind. No black hole should form. This is called the pair instability gap, and it means there should be no black holes between about 65 and 120 solar masses. But LIGO detected one with 85 solar masses. The most likely explanation is that this wasn't a first-generation black hole formed from a star. It was a second-generation black hole formed from the merger of two smaller black holes. In other words, LIGO detected a black hole merger where at least one of the merging black holes was itself the product of a previous merger. Let that sink in. We're now detecting the grandchildren of previous black hole collisions. The universe is building bigger and bigger black holes through a process of successive mergers. And in May 2023, LIGO and Virgo, along with the Kagra detector in Japan, detected the most massive black hole merger yet observed. The two black holes had masses of 85 and 66 solar masses, and they merged to create a final black hole of 142 solar masses, radiating away 9 solar masses as gravitational waves. This is significant because 142 solar masses puts the final black hole right in the middle of what's called intermediate mass range. We know stellar mass black holes exist. They form from stars. We know supermassive black holes exist. They sit at the centers of galaxies and can have masses of millions or billions of suns. But intermediate mass black holes have been elusive. This merger gave us definitive proof that they exist and showed us at least one way they can form, through successive mergers of smaller black holes. But here's what keeps me up at night. Every merger LIGO has detected so far happened millions or billions of years ago. The gravitational waves have been traveling through space for all that time, carrying the story of these cosmic catastrophes. What's happening right now in those distant galaxies? Have those black holes merged again with other black holes? Are they in the process of falling into supermassive black holes at galactic centers? We have no way of knowing. We're always watching the past, hearing echoes of cosmic violence that happened long before humans existed. Let's dive deeper into the physics of what actually happens during a black hole merger. Because when you really understand it, it's not just fascinating, it's beautiful. Einstein's field equations of general relativity are notoriously difficult to solve. They're a set of 10 interlinked, nonlinear partial differential equations that describe how matter and energy curve spacetime, and how that curved spacetime tells matter how to move. For most of the century after Einstein published his theory, physicists could only solve these equations for special simple cases. The Schwarzschild solution for a single, non-rotating black hole. The Kerr solution for a single rotating black hole. But two black holes orbiting and merging? That was too complex. The problem is that general relativity is nonlinear. That might sound like technical jargon, but it has profound implications. In linear theories, you can add solutions together. If you know how one charge creates an electric field, and you know how another charge creates an electric field, you can just add those fields together to get the field from both charges. But gravity isn't linear. Two black holes don't just create the sum of their individual gravitational fields. The fields interact with themselves in complex ways. Gravity gravitates. Space-time curvature creates more space-time curvature. This means you can't solve Einstein's equations for two black holes using pencil and paper. You need computers. Powerful computers running sophisticated numerical simulations. For decades, physicists tried and failed to simulate black hole mergers. The equations were too unstable. Small numerical errors would grow exponentially, causing the simulations to crash before the merger completed. Then, in 2005, 3 groups of scientists independently achieved a breakthrough. Physicist Franz Pretorius at Princeton developed a new mathematical technique for handling the equations. Almost simultaneously, teams at NASA Goddard and the University of Texas cracked the problem using different methods. Suddenly, we could simulate black hole mergers from start to finish. What these simulations revealed was stunning. The merger isn't a gentle process. The two event horizons don't just smoothly blend together. They collide, create a wildly distorted common horizon covered in ripples and bulges, then violently radiate away the distortions as gravitational waves. The simulations showed something else remarkable. The merger produces a kick when two black holes of unequal mass merge at an angle. With different spins, the asymmetric emission of gravitational waves creates a net momentum. The final merged black hole gets kicked, sometimes at speeds up to thousands of kilometers per second. Imagine that an object containing 100 times the mass of our Sun, where escape velocity from the surface exceeds the speed of light, getting kicked across space at thousands of kilometers per second. Some of these kicks are so powerful that the merged black hole can be ejected from its host galaxy entirely, flung out into intergalactic space. There are probably wandering black holes roaming the space between galaxies right now, exiles kicked out during violent mergers billions of years ago. But let's talk about something even stranger. What happens to information during a black hole merger? This is one of the deepest mysteries in physics. According to quantum mechanics, information cannot be destroyed. If you know the exact quantum state of a system at one time, the laws of physics allow you to calculate its exact state at any future or past time. Information is conserved. But black holes seem to violate this principle. Anything that falls into a black hole, whether it's a star, a planet, or your physics textbook, seems to be destroyed. The information about its exact quantum state disappears beyond the event horizon and eventually gets destroyed at the singularity. This led to what Stephen Hawking called the black hole information paradox. If information can be destroyed, quantum mechanics as we understand it is wrong. If information cannot be destroyed, we need a mechanism for how black holes preserve it. Hawking initially argued that information was indeed destroyed, violating quantum mechanics. But later in his life, he changed his mind, proposing that information might be encoded on the event horizon and eventually released in Hawking radiation, the quantum mechanical radiation that black holes emit. Now here's where it gets truly wild. When two black holes merge, they bring their information with them. The final black hole must somehow encode all the information from both original black holes. But how? Where does it go? How is it preserved? We don't know. This is one of the great unsolved problems in theoretical physics. Some physicists believe that the information is encoded in subtle correlations in the Hawking radiation. Others think that our understanding of space-time breaks down inside black holes, and information is preserved in ways we can't yet imagine. Some even propose that information might escape through wormholes to other universes. When two black holes merge, they're not just colliding. They're forcing us to confront the deepest questions about the nature of reality, the relationship between quantum mechanics and gravity, and the ultimate fate of information in our universe. So far, we've been talking primarily about stellar mass black holes, those formed from collapsed stars, with masses ranging from a few times to maybe 100 times the mass of the Sun. But there's another class of black holes out there, supermassive black holes. And when these merge, things get even more interesting. Almost every large galaxy has a supermassive black hole at its center. The Milky Way has one called Sagittarius A*, pronounced Sagittarius S*, with a mass of about 4 million suns. Our neighboring Andromeda galaxy has one with about 100 million solar masses. Some galaxies have black holes with billions of solar masses. How did these monsters form? We're not entirely sure. They're too massive to have formed from single stars. The most likely explanation involves a combination of mechanisms. Maybe they started from very massive stars in the early universe, then grew by accreting gas and dust, and by merging with other black holes over billions of years. And here's the thing. Galaxies merge. all the time. When two galaxies collide, and collide is actually misleading because stars are so far apart that individual stars rarely hit each other. The supermassive black holes at their centers eventually sink toward the center of the merged galaxy. They form a binary pair and begin the long, slow spiral toward merger. But there's a problem. It's called the final parsec problem. When two supermassive black holes get within about 1 parsec, 3.26 light-years of each other, they've already interacted with and ejected most of the nearby stars and gas. Without those interactions, they lose energy very slowly, and the remaining spiral toward merger could take longer than the age of the universe. Yet we see plenty of merged galaxies with single central black holes. Something must be helping these supermassive black holes overcome the final parsec problem and merge. Maybe there's more gas than we think. Maybe interactions with a third black hole help. Maybe something about the dynamics we don't understand is at play. Whatever the mechanism, supermassive black holes do merge. And when they do, the gravitational waves they produce are different from those of stellar mass black holes. Remember, the frequency of gravitational waves from a merger depends on the mass of the black holes. Stellar mass black hole mergers produce waves with frequencies of tens to hundreds of hertz, right in the range that LIGO can detect, similar to the frequency of sound waves we can hear. But supermassive black hole mergers produce much lower frequency waves, millihertz to microhertz. These frequencies are too low for ground-based detectors like LIGO to detect. Earth-based detectors are limited by seismic noise and other low-frequency interference. So how do we detect supermassive black hole mergers? The answer: we go to space. The European Space Agency, with contributions from NASA, is developing a space-based gravitational wave detector called LISA, the Laser Interferometer Space Antenna. LISA will consist of 3 spacecraft arranged in a triangle, with each side measuring 2.5 million kilometers. Yes, million. For comparison, the distance from Earth to the Moon is only about 384,000 kilometers. These spacecraft will track each other with extraordinary precision using lasers, detecting the tiny changes in distance caused by passing gravitational waves. Because the detector is so large and operates in the quiet of space, it will be sensitive to much lower frequencies than LIGO. LISA is scheduled to launch in the 2030s. When it does, it will open up a completely new window on the universe. It will detect supermassive black hole mergers happening millions or billions of light years away. It will tell us how these massive objects formed and evolved. It will test general relativity in regimes we've never been able to probe before. But here's something even more exciting. There's another way to detect supermassive black hole mergers, and we're already doing it. Pulsars are rapidly rotating neutron stars that emit beams of radio waves from their magnetic poles. As they rotate, these beams sweep across Earth like a lighthouse, creating pulses of radio emission with incredible regularity. Some pulsars are so regular that they rival atomic clocks in their precision. Now imagine gravitational waves from supermassive black hole mergers passing through our galaxy. These waves would stretch and squeeze spacetime, subtly changing the distances between Earth and distant pulsars. This would cause tiny, correlated changes in the arrival times of pulses from multiple pulsars. By carefully timing an array of pulsars spread across the sky, we can use them as a galaxy-sized gravitational wave detector. This is called a pulsar timing array, and several collaborations around the world are doing exactly this. In 2023, multiple pulsar timing array collaborations announced evidence of a gravitational wave background, a sort of hum of overlapping gravitational waves from countless supermassive black hole mergers happening throughout the universe. It's not a single clear signal like LIGO detects, but rather a stochastic background, like hearing the overlapping conversations in a crowded room. Think about what this means. We're now using the galaxy itself as a detector. Neutron stars scattered across tens of thousands of light years, all acting as precision clocks. allowing us to detect space-time ripples from the most massive collisions in the universe. Let's talk about something truly speculative but fascinating: primordial black holes. All the black holes we've discussed so far formed from collapsed stars or through successive mergers of stellar black holes. But there's another possibility. In the first fraction of a second after the Big Bang, when the universe was incredibly hot and dense, random quantum fluctuations could have created regions of slightly higher density. If these density fluctuations were large enough, they could have collapsed directly into black holes before the universe expanded and cooled. These hypothetical primordial black holes could have any mass. Some might be incredibly tiny, with masses less than an asteroid. Others could be massive. And if they exist, they would have been around since the very beginning of the universe. Here's where it gets interesting. Primordial black holes might explain dark matter. Dark matter is the mysterious substance that makes up about 85% of the matter in the universe. We know it exists because we can observe its gravitational effects, but we've never detected it directly. It doesn't emit, absorb, or reflect light. What if dark matter isn't some exotic particle? What if it's just primordial black holes? Black holes don't emit light either, and they definitely have mass and gravity. This idea has been around for a while, but it's been difficult to test. However, gravitational wave detections might provide clues. If some of the black hole mergers LIGO detects involve black holes with masses or properties that don't fit stellar formation models, they might be primordial. But here's something even stranger. What if black holes can merge with other types of exotic objects? There are hypothetical objects called boson star-stable configurations of a special type of particle field held together by their self-gravity. Unlike black holes, boson stars don't have event horizons or singularities, but they could be very compact and massive. If a boson star merged with a black hole, or if two boson stars merged with each other, they would produce gravitational waves. But the gravitational wave signal would be different from a black hole merger, with distinctive features that could tell us we're seeing something exotic. Similarly, some theories suggest the existence of gravastars objects that might form instead of black holes under certain conditions, with a strange equation of state for matter at extreme densities. Or wormholes, hypothetical tunnels through space-time, connecting different regions of the universe, or even different universes. If any of these exotic objects exist and merge, LIGO and future detectors might be able to spot them. The gravitational wave signature would be a smoking gun, revealing that our universe is even stranger than we thought. But let's bring this back to something we're more confident about: intermediate mass black hole mergers. Remember, we have stellar mass black holes formed from stars, with masses up to maybe 100 suns. We have supermassive black holes at galactic centers, with millions to billions of solar masses. But intermediate mass black holes, those with hundreds to hundreds of thousands of solar masses, have been elusive. Why do we care about them? Because they might be the seeds that grew into supermassive black holes. Understanding how they form and evolve is crucial to understanding how the supermassive black holes we see today came to exist. Some of LIGO's detections, like that 142 solar mass black hole I mentioned earlier, are right in the intermediate mass range. These detections suggest that repeated mergers might be one way to build up black holes in this mass range. But there's another possibility: dense star clusters. In the centers of globular clusters ancient, dense collections of stars' black holes might sink to the center due to dynamical friction, interact, and merge. These environments could be factories for producing intermediate mass black holes through successive mergers. As our detectors get more sensitive and we detect more mergers, we'll build up a statistical picture of the black hole population in the universe. We'll learn how common different masses are, how black hole spins are distributed, and how often mergers happen at different cosmic epochs. Every detection is a piece of the puzzle, helping us understand the life cycle of black holes from formation to growth through mergers to eventual fate. Let me tell you about one of the most profound things we can do with black hole mergers. Test whether Einstein's theory of general relativity is actually correct. See, general relativity has passed every test we've thrown at it for over a century. It predicts the precession of Mercury's orbit. It predicts gravitational lensing. It predicts the expansion of the universe. It's been tested in laboratories, in solar system experiments, with binary pulsars, and with cosmological observations. But black hole mergers give us something special, a test of gravity in its most extreme regime. These are regions where space-time curvature is so intense that even small deviations from general relativity would show up in the gravitational wave signal. This is where the ring down becomes crucial. Remember, after two black holes merge, the resulting black hole is distorted, covered in ripples and bulges. It then radiates away these distortions as gravitational waves, eventually settling into a stable, stationary black hole. This ring-down process produces gravitational waves with specific frequencies and decay rates that depend only on the mass and spin of the final black hole. Here's the remarkable thing. The ring-down frequencies are determined by something called quasi-normal modes. These are like the resonant frequencies of a bell. When you strike a bell, it rings it. Specific frequencies determined by its size, shape, and material composition. A black hole also has characteristic frequencies at which it rings. In general relativity, these quasi-normal mode frequencies are precisely determined by the black hole's mass and spin. Nothing else matters. Two black holes with the same mass and spin, regardless of how they formed or what they're made of, will ring at exactly the same frequencies. This is a direct consequence of what's called the no-hair theorem. According to this theorem, black holes are uniquely characterized by just three properties: mass, spin, and electric charge. All other information, all the details about what fell in to form the black hole, is lost. The black hole has no hair, meaning no distinguishing features beyond those three numbers. When scientists analyze the ring down from detected mergers, they can test this prediction. Does the ring down actually have the frequencies general relativity predicts? Or are there deviations that might hint at new physics? So far, general relativity passes with flying colors. The observed ring down signals match the theoretical predictions beautifully. But we're just getting started. As we detect more mergers and our detectors become more sensitive, we'll be able to test general relativity with increasing precision. But here's something that will blow your mind. We can actually use the ring down to test something called black hole spectroscopy. Think about it like this. When atoms absorb or emit light, they do so at specific wavelengths determined by their energy levels. By analyzing the spectrum of light from a star, we can determine what elements it contains. This is spectroscopy, and it's one of the most powerful tools in astronomy. Black hole spectroscopy is analogous. The ring down of a black hole contains multiple frequencies overtones, like the harmonics you hear when you play a musical note. If we can detect multiple overtones in the ring down signal, we can use them to independently measure both the mass and spin of the final black hole. Moreover, we can check for consistency. If general relativity is correct, all the overtones should give us the same mass and spin values. If we get different values, that would be a sign of new physics, a deviation from Einstein's theory. The first clear detection of an overtone in a ring down was announced in 2023. This was a major milestone, opening the door to precise tests of the no-hair theorem and general relativity in the most extreme environments. But let's think about something even deeper. What if general relativity is wrong? Don't get me wrong, general relativity is almost certainly correct in most regimes. But we know it can't be the final theory. It's incompatible with quantum mechanics. At the singularity inside a black hole, general relativity predicts infinite curvature and infinite density, which probably means the theory is breaking down. We need a theory of quantum gravity, a theory that combines general relativity and quantum mechanics into a single, consistent framework. Candidates include string theory, loop quantum gravity, and various others. Each of these theories makes slightly different predictions about what happens in extreme gravitational environments. Gravitational wave observations of black hole mergers might give us the first hints about which of these theories, if any, is on the right track. A tiny deviation from general relativity in the ring-down signal, a subtle anomaly in how black holes merge, an unexpected distribution of black hole spins, any of these could be the clue that revolutionizes physics. We're living in extraordinary time. Every gravitational wave detection is not just an observation, it's an experiment, a test of our deepest theories about space, time, and gravity. And the universe is providing us with the ultimate laboratory. Cosmic catastrophes billions of light years away, violent enough to shake the fabric of space-time itself. Here's something fascinating. Some black hole mergers might produce light. I know what you're thinking. Black holes are black. Nothing escapes from inside the event horizon, not even light. So how could a black hole merger produce electromagnetic radiation? The answer lies in the environment around the black holes. When black holes orbit each other in the dense gas environment near a galactic center, they can be surrounded by accretion disks, swirling disks of hot gas spiraling into the black holes. This gas emits X-rays and other radiation. When the black holes merge, they could create a detectable electromagnetic signal. The first direct evidence of this came in 2019, when astronomers reported seeing a possible optical flare associated with a black hole merger. Detected by LIGO, the gravitational wave signal arrived at Earth on May 21, 2019, and then, 34 days later, a telescope monitoring supermassive black holes saw a sudden brightening in a galaxy matching the rough location of the gravitational wave source. The interpretation: when the two black holes merged, they created a violent disturbance in the surrounding accretion disk. Gas was heated, compressed, and ejected, producing a burst of light that we could see with optical telescopes. This observation, if confirmed, would be groundbreaking. It would mean we can observe black hole mergers in both gravitational waves and light, giving us two complementary views of the same event. This is what astronomers call multi-messenger astronomy. We've already seen the power of multi-messenger observations with the neutron star merger in 2017. Gravitational waves told us about the dynamics of the merger, the masses, spins, and orbit. Electromagnetic observations told us about the matter ejected, the heavy elements synthesized, and the geometry of the explosion. Together, they provided a complete picture that neither observation alone could give. Now imagine doing the same with black hole mergers. Gravitational waves tell us about the black holes themselves and test general relativity. Electromagnetic observations tell us about the environment, the accretion disks, and the broader astrophysical context. But here's where it gets really interesting. What about the cosmic environment of these mergers? When black holes merge in dense star clusters or near galactic centers, they're not alone. There are thousands or millions of stars nearby. There might be planets orbiting some of those stars. What happens to them when two black holes merge nearby? The gravitational waves would pass through the entire region, stretching and compressing everything in their path. For most objects, the effect would be tiny, far too small to feel or even measure. But if you were close enough, say within a few hundred Schwarzschild radii of the merging black holes, the tidal forces could be dramatic. Any planet unfortunate enough to be in the vicinity would be subjected to enormous tidal stresses. The side closer to the merger would be pulled harder than the far side. If close enough, the planet could literally be torn apart, spaghettified, as physicists colorfully put it. And if there happened to be life on that planet, well, that would be a very bad day indeed. The good news is that black hole mergers are rare enough, and space is vast enough, that the chances of a merger happening close enough to harm Earth are essentially zero. But let's think about something else. What if advanced civilizations use black hole mergers for some purpose? This might sound like science fiction, but stick with me. Black hole mergers release enormous amounts of more energy in a second than the sun produces in its entire lifetime. If a sufficiently advanced civilization could somehow harness even a tiny fraction of that energy, it would be transformative. Or consider this. The intense gravitational fields near merging black holes could be used for extreme time dilation effects. Remember, time passes more slowly in strong gravitational fields. If you could park a spacecraft near, but not too near, merging black holes, time inside the spacecraft would pass much more slowly than in the rest of the universe. You could, in principle, use this for time travel into the future. Or maybe advanced civilizations use gravitational waves themselves for communication. Gravitational waves travel at the speed of light and pass through matter almost completely unimpeded. A gravitational wave message would be nearly impossible to block or intercept. If you wanted to send a message across the galaxy without anyone eavesdropping, modulating gravitational waves might be the way to do it. These ideas are highly speculative, of course, but they illustrate an important point. Black hole mergers aren't just passive astronomical events we observe. They're dynamic, energetic processes that shape the universe and could, at least in principle, be relevant to advanced technologies we can barely imagine. Let's talk about where this field is going, because we're just at the very beginning of gravitational wave astronomy. LIGO and Virgo are currently being upgraded to improve their sensitivity. The next observing run, scheduled to begin in 2025, will push the detection range even further, allowing us to observe black hole mergers happening farther away and detect smaller or more distant events. But there are also new detectors coming online. Kagra in Japan is already operating, adding a fourth detector to the global network. India is building LIGO India, which will be operational in the next few years. These additional detectors will dramatically improve our ability to pinpoint the exact location of gravitational wave sources in the sky. Here's why location matters. Right now, when LIGO and Virgo detect a gravitational wave, they can only narrow down its location to a fairly large patch of sky, often hundreds of square degrees. That makes it hard for optical telescopes to follow up and look for electromagnetic counterparts. But with 5 or 6 detectors spread around the globe, we can triangulate the source much more precisely. We'll be able to tell optical telescopes exactly where to look within minutes of detecting a gravitational wave. This will revolutionize multi-messenger astronomy. Then there's LISA, the space-based detector I mentioned earlier. LISA will open up an entirely new frequency range, detecting supermassive black hole mergers and other low-frequency sources. The detections will be different from LIGOs in a fundamental way. LISA will observe mergers unfolding over weeks or months, rather than fractions of a second. Imagine being able to predict that 2 supermassive black holes will merge next Tuesday. Telescopes around the world and in space could be ready, watching the event unfold in real time across the electromagnetic spectrum. We'd see the prelude, the merger, and the aftermath in exquisite detail. But here's something even more ambitious: the Einstein telescope. This is a proposed next-generation ground-based detector that would be built underground in Europe, with arms 10 kilometers long instead of LIGO's 4 kilometers. It would be about 10 times more sensitive than current detectors. What does that mean in practice? Remember, the volume of space a detector can observe scales with the cube of its sensitivity. 10 times more sensitive means it can detect sources 10 times farther away, which means it can observe 1,000 times more volume. The Einstein telescope could detect tens of thousands of black hole mergers per year. With that kind of statistical power, we could map out the entire population of black holes in the universe. We'd understand how black holes form, how they evolve, how often they merge, and how this has changed over cosmic history. And there's Cosmic Explorer, An even more ambitious concept for the United States: detectors with arms 40 kilometers long. At that sensitivity, we could detect stellar mass black hole mergers anywhere in the observable universe. We'd be able to trace the history of black hole formation back to the very first stars that formed after the Big Bang. But perhaps the most exciting possibility is detecting something completely unexpected. Every time we've opened a new window on the universe, we've been surprised. When Galileo first turned a telescope to the sky, he didn't just see what people expected more clearly. He saw things no one had imagined: the moons of Jupiter, the phases of Venus, the individual stars in the Milky Way. When radio astronomy began, astronomers expected to study thermal emission from stars and gas. They didn't expect to discover pulsars, quasars, and the cosmic microwave background. When X-ray astronomy began, no one predicted that the universe would be so rich in high-energy phenomena, black holes, accreting matter, neutron stars colliding, galaxy clusters filled with superhot gas. Gravitational wave astronomy is still in its infancy. We've detected a few dozen events. We've confirmed that black holes merge, that neutron stars merge, that general relativity works in extreme regimes. But what haven't we seen yet? Maybe there are sources we haven't imagined. Exotic objects that don't fit into any current theoretical framework. Signals from the early universe, from cosmic strings or phase transitions in the first moments after the Big Bang. Maybe even something from beyond our universe, if multiple universes exist and can interact gravitationally. This is the adventure we're on. Every improvement in detector sensitivity, every new detector that comes online, every year of observation brings us closer to discoveries that will transform our understanding of reality. And you get to witness it. Right now, at this moment in history, humanity is learning to hear the universe. We're no longer just watching the cosmos passively. We're listening to it sing. Let's step back from the physics for a moment and think about what all this means. Because black hole mergers aren't just interesting astrophysical events. They force us to confront deep questions about the nature of reality itself. First, consider what it means that space-time is dynamic. For most of human history, people thought of space and time as fixed stages on which events play out. Space was just the emptiness between things. Time was just the ticking of a cosmic clock. Einstein showed us that this is completely wrong. Space and time are woven together into space-time, and space-time is a physical entity that can bend, stretch, ripple, and even tear. When two black holes merge, space-time itself is the protagonist. It's not just the stage, it's the main actor. This has profound implications. It means that the geometry of the universe, the very structure of space and time, depends on matter and energy. The universe is not static, but dynamic, changing, and evolving. You, sitting there watching this video, are bending space-time right now. You're creating a tiny indentation in the fabric of reality just by having mass. Second, think about what black holes tell us about the limits of knowledge. The event horizon of a black hole is a boundary beyond which information cannot escape. Once something crosses the event horizon, it's forever cut off from the rest of the universe. We can never know what's happening inside. We can never retrieve information about what fell in. This isn't just a practical limitation of our technology. It's a fundamental feature of the universe. There are things we cannot know, not because we're not smart enough or don't have good enough instruments, but because the structure of space-time itself prevents us from knowing them. This raises deep questions. If information that falls into a black hole is lost, what does that mean for the nature of physical law? If information can be destroyed, then the future is not determined by the past. The universe becomes fundamentally unpredictable in a way that goes beyond quantum uncertainty. Or if information is somehow preserved, encoded on the event horizon or in Hawking radiation, then black holes are far stranger than we imagine cosmic hard drives, storing every bit of information about everything that ever fell in, encrypted in a code we don't yet understand. Third, consider what black hole mergers tell us about the violent history of the universe. The universe is not peaceful. It's not static. It's filled with catastrophic events, stars exploding, galaxies colliding, black holes merging. And these violent events aren't rare exceptions. They're happening constantly, everywhere, throughout cosmic history. The atoms in your body were forged in stellar furnaces and supernova explosions. The gold in any jewelry you're wearing was created in neutron star mergers. You are literally made of stardust, debris from cosmic catastrophes. Black hole mergers are part of this ongoing cosmic violence. There are moments when the universe itself screams, releasing more energy in a second than most stars produce in their entire lifetimes. And we're now able to hear those screams echoing across billions of light years. What does it mean that we live in such a violent universe? It means that destruction and creation are intimately linked. New things emerge from the ruins of old things. Black holes merge and create larger black holes, which might eventually merge again. This process has been going on for billions of years and will continue for billions more. Fourth, think about the cosmic perspective that gravitational wave astronomy gives us. When LIGO detects a merger, it's detecting an event that happened millions or billions of years ago. The gravitational waves have been traveling through the expanding universe all that time, carrying information about a cosmic catastrophe that occurred when the universe was younger, when Earth didn't exist, when life hadn't yet emerged. Those gravitational waves pass through empty space, through clouds of gas and dust, through forming galaxies and stars, through planetary systems. They pass through Earth itself, through mountains and oceans and cities, and you, barely noticing any of it, carrying their message intact. And then, after all that time and all that distance, they arrived at precisely the moment when humanity had developed the technology to detect them. We were there, listening, when the universe whispered its secrets. What are the odds? In all of cosmic history, in all the vastness of space, this merger happened and we heard it. If humans had lived a century earlier, we would have missed it. If we live a few more decades, we'll have detectors sensitive enough to hear thousands of such events. We're living at a special moment in cosmic history, the moment when intelligent life on one small planet learned to hear gravitational waves. That's not just a scientific achievement, it's a milestone in the universe's awakening to itself. Because here's the thing, we're not separate from the universe, we're part of it. We're how the universe comes to understand itself. We're made of atoms forged in stars, arranged in patterns complex enough to contemplate our own origins. When we detect gravitational waves from merging black holes, we're observing one part of the universe, one set of massive objects billions of light years, using another part of the universe, the complex arrangements of atoms and energy we call instruments and brains. The universe is observing itself, studying itself, understanding itself through us. Let's take a journey into the far future. What role will black hole mergers play in the ultimate fate of the universe? According to our best current understanding, the universe will continue expanding forever, accelerating due to dark energy. Galaxies will move apart, eventually becoming isolated island universes, unable to see or interact with each other. Within each galaxy, stars will continue to form, burn, and die. But the supply of gas for making new stars is finite. Eventually, perhaps 10 trillion years from now, the last stars will burn out. The universe will enter what's called the degenerate era, dominated by the slowly cooling corpses of dead stars, white dwarfs, neutron stars, and black holes. But even dead stars don't last forever. On timescales of 1,030 years or more, matter itself may decay. Protons might spontaneously fall apart. White dwarfs and neutron stars would gradually evaporate, their matter dissipating into space as radiation and individual particles. What would remain? Black holes. Black holes are the most stable objects in the universe. They don't decay through any normal process. They just sit there, eternal and unchanging. But they're not quite immortal. Stephen Hawking discovered that black holes actually do radiate. Quantum effects near the event horizon cause them to emit radiation and gradually lose mass. This Hawking radiation is incredibly weak, so weak that for any stellar mass or larger black hole, it's completely negligible compared to the energy they absorb from the cosmic microwave background. But in the far future, when the universe is cooled and emptied, Hawking radiation becomes significant. Black holes will slowly evaporate. A stellar mass black hole will take about 1,067 years to evaporate. A supermassive black hole might take 10,100 years or more. But before they evaporate, black holes will merge. Remember, galaxies contain many black holes. Over time, dynamical interactions will cause them to sink toward galactic centers and merge with the central supermassive black hole. This process will continue for trillions of years, gradually building larger and larger black holes. Eventually, perhaps 1,020 years from now, each galaxy will contain a single merged black hole, the remnant of all the matter that was once in that galaxy. But the story doesn't end there. Galaxies themselves are gravitationally bound into clusters. Over enormous timescales, the black holes at the centers of galaxies within a cluster will gradually spiral toward each other and merge, creating even more massive black holes. This process will play out over timescales almost impossible to comprehend. But eventually, after 1,030 years or more, we might be left with a universe containing only a few supermassive black holes, each one the merged remnant of an entire galaxy cluster. And then slowly, over timescales of 10,100 years, even these black holes will evaporate through Hawking radiation. The universe will be left with nothing but a cold, diffuse soup of particles and radiation, forever expanding, forever cooling, approaching absolute zero. This scenario, the heat death of the universe, is our best guess at the ultimate fate of everything. It's not a pleasant picture. It's a universe that ends not with a bang, but with a whimper. All structure dissolved, all complexity lost, nothing remaining but cold emptiness. But here's something to think about. We don't know for sure. Our understanding of physics has limits. We don't understand dark energy. We don't have a theory of quantum gravity. We don't know if protons decay. We don't know if the laws of physics might change over ultra-long timescales. Maybe the universe is cyclic, with big bangs and big crunches repeating forever. Maybe black holes are seeds for new universes, with new big bangs occurring inside them. Maybe vacuum decay will eventually occur, changing the fundamental constants and laws of physics. Maybe something we haven't imagined will happen. But one thing seems certain. Black holes and their mergers will play a crucial role in the universe's far future, just as they have in its past and present. Every black hole merger we detect with LIGO is a glimpse not just of distant space, but of deep time. It's a process that has been happening since the first stars formed. That's happening now throughout the universe, and that will continue until the last black holes evaporate in the unimaginably distant future. We're witnessing part of a story that spans the entire history of the universe, from beginning to end. So we've journeyed through the physics of black hole mergers, from the basics of general relativity to the far future of the universe. But let's bring this back to you, sitting there right now, watching this video. What does any of this have to do with your life? On one level, nothing. Black hole mergers happen billions of light years away. They don't affect your daily life. Whether or not two black holes merge somewhere in the distant universe makes no difference to your job, your relationships, your plans for tomorrow. But on another level, this knowledge changes everything. Think about the fact that right now, gravitational waves from countless cosmic events are passing through your body. Waves from black hole mergers, neutron-star collisions, supernova explosions. The fabric of space-time is rippling around you, stretching and squeezing you by amounts far too small to feel, but real nonetheless. You are not separate from the cosmos. You are embedded in it, part of it. The same laws of physics that govern black hole mergers govern the beating of your heart, the firing of neurons in your brain, the chemical reactions that keep you alive. The atoms that make up your body were created in cosmic violence. The iron in your blood was forged in supernova explosions. The calcium in your bones was created in stellar cores. You are made of the universe, and the universe is in you. Black hole mergers remind us of our cosmic context. They show us that we live in a dynamic, evolving universe filled with events of incomprehensible power. They demonstrate that the universe operates on scales both far larger and far smaller than human experience. But they also show us something inspiring. We can understand these events. With nothing but mathematics, careful observation, and creative thought, humans have figured out how black holes form, how they merge, what gravitational waves are, and how to detect them. We live on a small planet orbiting an ordinary star in a typical galaxy among hundreds of billions of galaxies. We've existed as a species for only a few 100,000 years less than a blink in cosmic history. And yet we've developed the ability to hear echoes of the most violent events in the universe, events that happened billions of years ago and billions of light years away. That's not just impressive, it's almost miraculous. It means that intelligence, consciousness, and curiosity are powerful forces in the universe. It means that understanding is possible. It means that the universe can be known. Every time LIGO detects a gravitational wave, it's a victory for human curiosity and ingenuity. It's proof that we're not helpless in the face of cosmic immensity. We can observe, measure, understand. And this understanding isn't just academic. The same scientific method that revealed gravitational waves has given us modern medicine, technology, and our understanding of ourselves. The same curiosity that drives us to study black holes drives us to cure diseases, explore our planet, create art, and build civilizations. Black hole mergers also give us perspective on our problems. Yes, your life has challenges. Yes, the world has serious issues that need addressing. But when you zoom out and see the universe for what it really is, this vast, ancient, violent, beautiful cosmos, it puts things in perspective. The universe doesn't care about human concerns. It doesn't care about our politics, our anxieties, our social media dramas. It operates on its own timescales and by its own rules. Black holes merge, whether we notice or not. Galaxies collide. Stars are born and die. The cosmic dance continues. There's something oddly comforting about that. It reminds us that our individual problems, as important as they feel, are temporary. The universe has been here for 13.8 billion years and will continue for trillions more. You're part of something much larger than yourself. But, and this is important, that doesn't mean your life doesn't matter. It means the opposite. In this vast, mostly empty, mostly unconscious universe, consciousness is rare and precious. The fact that matter can arrange itself into patterns that think, that feel, that wonder about black holes and gravitational waves, that's extraordinary. You are a way for the universe to know itself. You're not just in the universe. You're part of how the universe becomes aware of its own existence. When you learn about black hole mergers, you're participating in the universe's self-discovery. So yes, black hole mergers happen billions of light years away. But the knowledge of them, the understanding of them, exists right here, in your mind. The cosmos reaches across space and time to tell you its story, and you're capable of hearing it? That makes you special. That makes your existence meaningful. You're a temporary pattern of atoms that has somehow become complex enough to contemplate the very fabric of space-time. As we near the end of this journey, let's talk about what we still don't know. Because as much as we've learned, the biggest questions remain unanswered. First, what happens at the singularity? When matter collapses past a certain point, general relativity predicts that it crushes down to infinite density at a single point of singularity. But infinity is a red flag in physics. It usually means your theory is breaking down, that you're missing something important. We need a theory of quantum gravity to understand what really happens at the center of a black hole. Does the singularity actually exist, or does quantum mechanics prevent it? Is there something inside black holes we can't imagine? Some theories suggest that the singularity might be replaced by a tiny but finite region where space and time become quantum foam, a seething, chaotic mixture where the usual concepts of space-time break down entirely. Other theories propose that black holes might contain baby universes. The singularity might be a portal to another space-time, another cosmos. When two black holes merge, maybe two universes are somehow combined. We have no way to test this, but it's a fascinating possibility. Second, what is the information paradox really telling us? The tension between general relativity and quantum mechanics reaches its peak with the black hole information paradox. If information that falls into a black hole is truly lost, quantum mechanics is violated. If it's preserved, we need a mechanism, and we don't have one yet. Recent work suggests that information might be encoded in subtle correlations in Hawking radiation, or in the quantum entanglement between particles inside and outside the event horizon. But we don't have a complete understanding. This might be the biggest clue we have about how to combine quantum mechanics and gravity into a single theory. Solving the information paradox might revolutionize physics. Third, how do supermassive black holes form? We see supermassive black holes with billions of solar masses in the early universe, less than 1 billion years after the Big Bang. How did they grow so large so quickly? The standard picture that they formed from stellar mass black holes and grew through accretion and mergers might not provide enough time. Maybe supermassive black holes formed directly in the early universe from the collapse of massive gas clouds. Maybe they formed from primordial black holes. Maybe something about the early universe we don't understand allowed rapid growth. This is an active area of research. Gravitational wave observations from LESA will help us understand the merger history of supermassive black holes, providing crucial clues. Fourth, are there other types of compact objects? We're confident that black holes exist. We've detected their mergers. But what if there are other types of ultra-compact objects we haven't discovered yet? Theories predict the possibility of gravastars, boson stars, Prion stars, and other exotic objects. If any of these exist, they might merge and produce gravitational waves with distinctive signatures. As our detectors become more sensitive, we might discover that the universe is even stranger than we thought. Every time we've looked at the universe with new eyes, we've been surprised. Gravitational wave astronomy is still young. Surprises almost certainly await. Fifth, can we detect gravitational waves from the Big Bang? In the first fraction of a second after the Big Bang, the universe underwent a period of exponential expansion called inflation. If inflation occurred, it would have produced gravitational waves, primordial gravitational waves, embedded in the fabric of spacetime itself. These gravitational waves would still be present today as a faint background signal. Detecting them would give us a direct window into the universe when it was less than a second old, probing energy scales and physics we can't recreate in any laboratory. Several experiments are trying to detect these primordial gravitational waves by looking for their imprint on the cosmic microwave background radiation. Success would be revolutionary, confirming inflation and giving us clues about the physics of the very early universe. Sixth, is general relativity the final word on gravity? Einstein's theory has passed every test so far, including extreme tests from black hole mergers. But we know it can't be complete. At the quantum level, general relativity doesn't work. We need a quantum theory of gravity. String theory, loop quantum gravity, and other approaches try to provide this, but we don't yet know which, if any, is correct. Moreover, the fact that we need dark matter and dark energy to explain astronomical observations suggests that either there's a lot of stuff we haven't detected, or our theory of gravity needs modification. Some physicists have proposed modified theories of gravity that might eliminate the need for dark matter or dark energy. Gravitational wave observations provide stringent tests of these theories. So far, the observations support standard general relativity, but the search continues. Finally, are we alone? This might seem like a strange question to end with, but bear with me. Advanced civilizations, if they exist, might be able to manipulate black holes or use them for engineering projects we can barely imagine. Could an advanced civilization create artificial black hole mergers to send signals? Could they use black holes for power generation or computation? Could they survive the far future by using black holes? We have no evidence of this, of course, but it's worth considering. As we detect more and more gravitational wave signals, we should keep an open mind about the possibility that some might be artificial, the products of technology, rather than natural astrophysical processes. The universe is vast, old, and full of possibilities. We've only just begun to listen to it with gravitational wave detectors. Who knows what we might hear? Let's talk about what comes next, not just for gravitational wave astronomy, but for our understanding of the cosmos. The field of gravitational wave astronomy is barely a decade old. We're in an era similar to the early days of optical astronomy, when Galileo first turned a telescope to the sky. We've made some discoveries, confirmed some theories, but we're still learning how to use this new tool. Over the next few decades, we'll see dramatic improvements. Ground-based detectors will become more sensitive. LISA will launch and open up the low-frequency spectrum. New detector concepts, like atom interferometers or lunar-based detectors, might push sensitivity even further. With each improvement, we'll detect more sources, observe them in greater detail, and probe new regimes of physics. The number of known black hole mergers will grow from dozens to thousands to millions. This wealth of data will allow us to answer questions we can't address with current observations. We'll map the complete population of black holes across cosmic time. We'll trace how black holes form, evolve, and merge throughout the history of the universe. We'll test general relativity with unprecedented precision. Every merger is an experiment, a chance to see if Einstein's theory holds up in the most extreme conditions. If deviations from general relativity exist, we'll find them. We'll detect new types of sources. Maybe primordial black holes, maybe exotic compact objects, maybe gravitational waves from the Big Bang itself. Each new type of source will open new windows on physics and cosmology. But beyond the specific discoveries, there's something deeper happening here. We're developing a new sense, a new way of perceiving the universe. For billions of years, life on Earth has evolved to detect electromagnetic radiation light. Our eyes and the instruments we build are fundamentally light detectors. But now we're learning to detect gravitational radiation. We're teaching ourselves to hear gravity. We're expanding our perceptual abilities beyond what biology gave us. This is part of a larger pattern in human history. We've repeatedly expanded our senses through technology. Microscopes let us see the very small. Telescopes let us see the very distant. Radio receivers let us detect electromagnetic waves our eyes can't see. Each expansion of our senses has revolutionized our understanding. The microscope revealed the world of cells and microbes. The telescope revealed the immensity of the cosmos. Radio astronomy revealed pulsars, quasars, and the cosmic microwave background. Gravitational wave detectors are the latest step in this journey. They're letting us perceive aspects of reality that were previously hidden. And like every previous expansion of our senses, this one will change us. It will change how we think about the universe. It will change what questions we ask. It will change what we consider possible. But here's the thing. This expansion of knowledge isn't happening in isolation. It's part of humanity's broader awakening to the nature of reality. Over the past few centuries, we've learned that Earth isn't the center of the universe. We've learned that the sun is one star among hundreds of billions. We've learned that the Milky Way is one galaxy among hundreds of billions. We've learned that the universe is 13.8 billion years old, vastly larger and older than anyone imagined. We've learned that matter is made of atoms, that atoms are made of particles, that particles are excitations of quantum fields. We've learned that space and time are unified into space-time, that space-time can curve and ripple, that black holes exist where space-time becomes so warped that it tears. Each of these discoveries has been humbling. Each one has shown us how small we are, how recent our existence is, how little of the universe we occupy. But each discovery has also been empowering, because each one represents something we figured out. Each one is a victory of human intelligence over cosmic mystery. Each one proves that the universe, however vast and strange, can be understood. Black hole mergers are part of this story. They're among the most extreme events in the universe, releasing more energy than all the stars in the observable universe combined. And we can hear them. We can analyze them. We can understand them. That should fill you with awe, but also with hope. It means that understanding is possible. It means that consciousness and intelligence matter in this universe. It means that you, a temporary pattern of atoms on a small planet, can nevertheless comprehend events of cosmic significance. We've covered a lot in these 3+ hours. Let me bring it all together. Can two black holes merge into one? Yes, absolutely. They spiral together, radiating gravitational waves until their event horizons touch and form a common horizon. The merged black hole rings down, settling into a stable configuration. In the process, a significant fraction of their combined mass is converted into gravitational wave energy pure space-time vibrations that ripple outward at the speed of light. We've detected dozens of these mergers. We've heard the sound of space-time being shredded and reformed. We've tested Einstein's theory in its most extreme regime and found it holds up beautifully. We've learned about the population of black holes in the universe and how they evolve through cosmic history. But more than that, we've opened a new window on the cosmos. We're no longer just watching the universe. We're listening to it. We're detecting events that produce no light, that are completely invisible to traditional astronomy. We're hearing the universe's secrets whispered across billions of light years and billions of years. And this is just the beginning. Better detectors are coming. More discoveries await. The field of gravitational wave astronomy will transform our understanding of the universe over the coming decades. But here's what I really want you to take away from this. You're part of this story. You're not a passive observer of the cosmos. You're an active participant in the universe's attempt to understand itself. The knowledge we've discussed about black holes, space-time, gravitational waves exists because humans like you cared enough to wonder, to question, to seek understanding. Every scientist who contributed to this field started as someone like you, watching videos, reading books, wondering about the cosmos. Rainer Weiss, Kip Thorne, Barry Barish, the founders of LIGO, were once students learning physics, amazed by the universe's mysteries. The next generation of discoveries will come from people who are students right now, or who haven't even been born yet. Maybe you'll be part of that. Maybe you'll help design the next generation of detectors, or analyze the data from future observations, or develop the theories that explain what we discover. Or maybe you won't work in science at all. That's fine too, because the value of this knowledge isn't just professional. It's existential. It changes how you see yourself and your place in the universe. You live in a cosmos that's 13.8 billion years old, 93 billion light years across, containing hundreds of billions of galaxies, each with hundreds of billions of stars. In that vast cosmos, black holes are constantly merging, releasing more energy than all the stars combined, shaking space-time itself. And you, made of atoms forged in stellar furnaces, living on a small planet, somehow have the ability to understand all of this. You're a way, for the universe to know itself. You're part of the cosmos that has become conscious and curious. That makes your existence meaningful. That makes your life matter. Not in a cosmic, universe-altering way, but in a profound, beautiful way. You're a temporary pattern of atoms that can think, feel, and wonder. You're part of the universe's story of awakening to itself. So keep wondering, keep questioning, keep learning. The universe has so many secrets left to reveal. We've barely scratched the surface of what's out there, what's possible, what remains to be discovered. Black hole mergers are just one piece of the puzzle. There's so much more. Dark matter, dark energy, quantum mechanics, consciousness, the nature of time, the origin of life, the possibility of other universes. Each mystery is an invitation to explore, to think, to discover. You're living at an extraordinary moment in cosmic history. The universe is 13.8 billion years old, and you're alive right now, at the moment when intelligence has developed enough to detect gravitational waves, to hear black holes collide, to probe the nature of space-time itself. That's not a coincidence. That's not meaningless. That's part of the universe's story, and you're part of it too. So thank you for joining me on this journey. Thank you for caring enough about black holes and gravitational waves to spend 3 hours learning about them. Thank you for being curious, for being willing to grapple with complex ideas, for wanting to understand the cosmos. The universe is vast, mysterious, and beautiful, and so are you for wanting to understand it. Keep looking up, keep listening, keep wondering.